So what we want to do now is we want to look a little bit about how shafts break and what they look like when they hit those failure modes. And so what I want to do is let's take a look at, so I have these little elements drawn on my shaft. I have an element A and an element B. And so now if I look at element A on the surface of the shaft, because I'm twisting, I've got these torques going here. Well, if I look at that element, especially along sides here, I'm going to be in a complete shear stress location. So I'm going to twist the thing, and all of the stress that's going to be applied to that is going to be purely in the shear stress, the parallel direction. Now, if I look at this element here, which is rotated slightly, you'll notice that, okay, well, if I map these stresses and on components on there, I'm going to have some parts of those stresses that are mapped pushing straight in, and I'm still going to have some that are mapped at a 45-degree angle. And for this kind of stuff that we're doing right now, don't worry about it if it doesn't really make a ton of sense as it is, because when we do 2D elements, we're really going to go into how this works. Basically, I'm showing this to you now because I want you to see a couple of different things. And the first one is that for this element that's, this element A that's not rotated, the maximum stress is going to be a shear stress coming right along our thing. And then if we look at this guy, this is a normal stress. And so how do we figure out the normal stress? Well, that's going to be the force divided by the area. And actually, if we look at this at 45 degrees, we're going to have a normal stress that's going to be equal to our maximum shear stress. And that should ring a bell, because when we were doing our stresses of the splice joints with the oblique cuts, and we had our normal and our shear, you'll remember that our maximum normal stress, at our maximum shear stress, our normal stress was going to be equal to that shear stress. And so why is any of this stuff important, and really what am I getting at? And I really am getting at talking about the failure modes. So element A, this guy right here, this guy's in pure shear. So all of the forces on that element are shearing forces. This element here, this element B, has tensile forces, compressive forces, and shear forces on it. So it's got that whole boat of tensile forces making it longer, compressive forces making it shorter, and then the shear forces. So what does that mean for us? So if I take a look at it here, so once again, I look at these elements, they're A and C here instead of A and B, but our maximum shear stress, well, that first element's in pure shear, it's just going to be TC over J. Our normal stress at this element that's rotated 45 degrees is also going to be TC over J. Once again, we're going to talk about this more when we talk about plane elements, but this is where we get into the more interesting stuff, and that's how it breaks. So ductile materials. So we've dealt with ductile materials before. What is a ductile material? It's a material that will stretch before it bends. So when we pulled on our dog bone, what happened? This guy got smaller and eventually broke. Ductile materials can fail in the plastic region because they can elastically deform, where a brittle material is weaker in tension than a ductile material, and so it could not elastically deform. So where this becomes interesting is how they fail. So a ductile material will generally fails in shear. And since a ductile material fails in shear, that means it's going to fail along that line. It's going to give us a clean break. A brittle material is weaker in tension than in shear, because in tension, as soon as it gets past that elastic region, it breaks. So since it is weaker in tension than in shear, a brittle material will break along this line. So brittle, ductile. So what does that look like in real life? So this is a ductile failure. What's interesting about that is you look at it, and that breaks the exact same way that a brittle piece of material would break in a normal load. And this is what it would look like in the Phineas-Olson machine. Because it's going to break along, right along this line, where it's weakest and shear. So now the brittle material is going to kind of corkscrew along that normal force. And so now if I bring up this slide here, you'll see it's got a corkscrew kind of break. This one's kind of neat because if you take a piece of chalk, grab it, and put torque on it and twist it, you'll get this, it's a corkscrewing kind of break. So it's kind of interesting. And so you can look at the material and figure out some stuff about it. Okay, is it ductile or brittle? Just by taking a look at how it's going to fail in that shear mode. Excuse me, in that torsional mode.